Hello, and welcome to another lecture for Unit 7, our unit on the mole. In order to complete this lecture, you need to know how to use Mole Island and do one-step and multi-step mole conversions. You also need your Unit 7 book and open up to page 13. So, reading page 13 and will give you details on what an empirical formula is and what a molecular formula is. So the big takeaways from the page: an empirical formula has been simplified, so it is the lowest possible whole number ratio, something like CH2O. You cannot reduce those subscripts any lower, like a fraction, whereas a molecular formula is going to be like glucose, C6H12O6. It tells us the actual number of atoms that you have to have in order to make up that compound. In glucose, you need 6 carbons, 12 hydrogens, 6 oxygens. Sometimes an empirical and molecular formula can be the same thing. So here's a couple more examples of empirical versus molecular formulas. Typically, these type of questions can come in multiple formats. They could be multiple choice, where you have to be able to recognize how to reduce subscripts to the simplest version. Other ways is to be able to match, have these correctly been reduced, which one's an empirical, which one's molecular. So you can see here, this column is all molecular formulas. H2O2. Those can both be reduced by 2, divided by 2. That gives you HO. Same for all of these. Okay, so these are all empirical molecular formulas. I'm sorry, and I have one out of place here. Sometimes the empirical and molecular formula are identical. You're not going to be able to reduce it any further, and it is also the actual true number of atoms in the molecule. Also like water, H2O. So what this lecture is going to focus on are the application-based longer problems for empirical and molecular formulas. And so all the notes that I'm going to go over are located for empirical formulas are located on page 14. So when you look at page 14, there are 3 detailed steps. There are lots of words. And so what I've done on my PowerPoint slide is just summarize, but I think it's very beneficial for you to actually pause the video, read page 14, and then resume it so that I can help summarize. So go ahead and pause the video and read through page 14 and highlight any important information that you might see. Okay, so you have read page 14, you've highlighted the important information, and I'm just going to reiterate it. So step number 1, you have to go from grams to moles. That in chemistry, always go to moles. That's your given go-to unit. The thing that is weird about this is we do not want you to round. Up until this point, you've heard us preach sig figs, sig figs, sig figs, and sig figs don't matter here. The entire point of this math is to arrive at a chemical formula like this, CH4. Okay, so we do not need sig figs here. If you happen to be given percent composition data, assume that you have 100 grams of your sample, and you can just directly change your percent sign to grams. Then, after you've converted everything to moles, you are going to divide by the smallest number of moles. Hopefully, this step yields you a whole number. And I always say to look for something within spitting distance. So we cannot just round our values up or down as we feel this time. So spitting distance, an example, 3.979 is close enough. It is basically 4. It is within spitting distance. Same for 4.012. Sure, these digits don't say 4.000, but this is close enough to 4. So a value that's not within spitting distance would be an example of having 3.252. That is not close enough for me to round down to 3, or 3.501, or 3.753. Okay? Anytime you have digits that are not just so stinking close to a whole number, you actually have to multiply. So for example, I don't know off the top of my head how to get it to a whole number, but we can try. So 3.75, if I type in my calculator, times 2, that gives me 7.5. that's still not close enough for me. So 3.753 times 3. That gives me 11.259. Also not close enough for us. 3.753 times 4. That gives me 15.012. This right here is close enough to a whole number. So because I multiplied this by the number 4, every other digit in our problem would have to be multiplied by 4 again. So I'll do an example of that as we move on through our examples. No big deal. But these are the steps that I'm following every single time. So I want to emphasize really quickly, if you do not know what's going on, like you have no idea where my steps are coming from, you have no idea why I'm doing the math that I'm doing, I really want you to keep your unit book out next to you, keep your notes out next to you. Will be like that's the best possible way for you to learn how to do these. Keep your notes with you. Eventually you will get to where you won't need to have your notes out next to you. Okay, so the first example problem I'm going to do is one that I actually assign in class for you to do as like a homework problem, just so that there's room for you to work the problem with me. So I'm looking at number 1 on page 16. Number 1 on page 16 says, a 2.67 gram sample of an unknown compound was found to contain 0.730 grams of sodium, 0.442 grams of nitrogen, and 0.1504 grams of oxygen. Calculate the empirical formula for this compound and name it. So the first step says to convert from grams to moles and do not round. So that's exactly what I'm going to do. So I have, for sodium, I have 0.730 grams of Na. For nitrogen, I have 0.442 grams of nitrogen. And for oxygen, I have 1.504 grams of oxygen. So what we're going to do now is just convert from grams to moles for each one of these elements that are supposed to be in my chemical formula. One thing I want to emphasize, up until now, when we have been doing gram to mole conversions, we've worked with nitrogen gas. And nitrogen gas, the chemical formula is N2. Same for oxygen gas, it's O2. This is a direct application of Brinkelhoff and our diatomic, sorry that my slides flip back and forth. This is a direct application of Brinkelhoff and using diatomic atoms. Well, nitrogen and oxygen are not by themselves as a compound here. They are actually within a bigger compound, so Brinkelhoff doesn't matter. So when I convert from grams to moles, I'm going to have 1 over 23. I'm going to have 1 over 14.01, and I'm going to have 1 over 16. So if you do not know where those values are coming from, you need to go back and watch my first video on how to do one-step mole conversions. So remember, the big kicker here, do not round. So my answer from dividing 0.730 divided by 23 gives me 0.3031739. I'm not rounding, keeping lots of digits. All right, so for nitrogen, I get 0.031549. And for oxygen, I get 0.094. That's what it gives me out of the calculator. All right, step number 2 tells me that I need to divide by the smallest number of moles. Oops, sorry. I need to divide by the smallest number of moles that I calculated. I keep doing that. Sorry, you guys. Okay, so when I look at my numbers, 0.0317, 0.0315, put 0.094, here is my smallest number of moles. So I'm going to divide all of my mole calculations by the smallest number of moles. Okay, again, don't round early. Hopefully this is going to give us a whole number, but I'm not going to round early just in case it doesn't. All right, so when I divide by the smallest, this gives me 1.006. This does give me 1, and this gives me 2.979. So here is where I look for spitting distance. If all of my values are within spitting distance, I'm in the clear. 1.00 is 1. 2.97 is 3. So now that I have whole numbers, my chemical formula is going to be NaNO3. And this is called sodium nitrate. And you should have learned how to name that in our Unit 5. Okay? All right. So the next one that I want to work, I want to look at number 2 on page 16. Number 2 says, a mysterious white powder was found at a crime scene. It was quantitatively analyzed, and its percent composition was determined to be 27.37% sodium, 1.20% hydrogen, and 14.30% carbon, with the remainder being oxygen. Calculate the empirical formula for this compound. Well, step 1, when I calculate an empirical formula according to page 14, says to convert grams to moles. Well, we were given percent signs. That's weird. But our notes also say to assume that we have a 100 gram sample and we can convert the percent signs directly to grams. So that tells me for sodium, I have 27.37 grams of sodium. For hydrogen, I'm sorry if you can hear my dogs barking, I have 1.20 grams of hydrogen. For carbon, I have 14.30 grams of carbon. And the last part of the problem says, and the remainder being oxygen. So this is where you have to do a little bit of problem solving. Okay, so in that problem solving, I assumed that my sample was 100% of a sample. And so for that reason, I can take 100 and subtract all of the other given amounts for my elements, and that's going to help me find the amount of oxygen I need. So that's 57.13 grams of oxygen. So that's what I'm going to use here in my gram to mole conversions. Again, I'm very sorry if you can hear my dogs, but if I pause the video, then I'll have to do all of this again. So we're just going to have to deal with it. All right, so here are 4 one-step gram to mole conversions. Very easy peasy. So if you want to pause the video and try this on your own, that's great. It's a great way to learn. You guys actually trying by yourself. If you still need my help, you can obviously resume. So gram to mole, gram to mole. So for sodium, 1/23. And that gives me 1.19. That's all the digits that it gives me. That's fine. 1/1.01. And that gives me, 1.1881. 1 mole, 12.01 grams. And that gives me, 1.1907. And last, 1/16, and that gives me 3.5706. All right, so there is all step number 1. Step number 2 says I need to divide by the smallest number of moles. So when I analyze 1.19, 1.18, 1.19, 3.57, here is my lowest number of moles, 1.1881. So again, hopefully this yields a whole number that is within spitting distance. If not, we're going to have to do a little multiplying to help us get to a whole number. So 1.19 divided by 1.1881 gives me 1.002. This gives me 1.1907. This gives me also 1.002, and this gives me 3.005. So all of these values are thankfully within spit distance. And so my chemical formula is going to be Na. There's one of those, one hydrogen, one carbon, but I'm going to have 3 oxygens. So here is sodium, and this is the polyatomic ion bicarbonate. So sodium bicarbonate. Okay. I didn't have to. I just didn't happen to work an example where you actually need to multiply in order to get to a whole number. And just because that happened in this example video doesn't mean that you won't come across it. If you want to go back and work, if you flip back the page to page 15, at the very top of page 15 of your unit book, it says example problem 2. This is a great problem for you to go back and try on your own, and you will have to multiply by something in order to get to a whole number. So I'll go ahead and tell you the answer to example problem 2 on page 15, and that is going to be Na2S2O3. So if you try to work this on your own, which I highly, highly, highly recommend, and you do not arrive at that answer, you need to come in and see one of your chemistry teachers face to face. Okay, so I'm going to cut this video off just so that it'll upload a little faster. You will need to go and watch part 2 for how to calculate molecular formulas. Okay, thank you for watching. Make sure that you are practicing on your own and keeping your notes out next to you so that you can grow in confidence. Thank you very much.